Good morning to one and all present here. So we are moving on to the day 4 session 2, and we are going to have the session by Dr. U. Chandrasekhar, who is the program director of Wipro 3D. He's going to talk about the IoT based manufacturing and design. So without much delay, let me invite Professor Levin Varghese for introducing the speaker.
Good morning. Good morning all. I welcome Dr. U. Chandrasekhar, Program Director at Wipro 3D Bangalore for the program. Sir has extensive experience in mechanical analysis, additive manufacturing, and structural integrity evaluation of gas turbines. Sir has worked as additional director in DRDO. Led a large group of scientists in Central Institute of Aviation, Moscow for flying test beds trials of a development aero engine. I welcome most heartedly. Welcome you, sir. Welcome for the program. Thank you, sir.
Okay, thank you so much, Professor Shanmugesh, and thank you, the faculty members of Vishwajyoti College of Engineering and Technology. And it's my pleasure to share my insights with reference to additive manufacturing and IoT enablement. And incidentally, we at Wipro 3D have been very closely associated with these digital manufacturing technologies for about 7 years. So before actually getting into the world of additive manufacturing and the potential usages of integrating IoT into this, let me take your attention to one of the new items from June 2020, wherein BMW announced that they are setting up a dedicated additive manufacturing campus in Germany with complete focus on leveraging the advantages of metal, composite, and polymer 3D printing technology with reference to automotive sector. If you see in this plant, BMW has set up 51 systems, some capable of handling photopolymer materials, other metallic materials like nickel, titanium, steels, cobalt, chrome alloys, and a few which can deal with composites. The entire facility is just manned by about 7 or 8 engineers, and it works 24/7, churning out the parts which are required for BMW automotive systems, which are world famous, and also producing the spare parts just in time on demand for their legacy cars. And last but not the least, helping their geographically distributed teams across the world in converting their designs and concepts into physical parts. So it's a very, very futuristic kind of an approach for extremely competitive extremely competitive sector of automobile engineering. And if you contrast the scenario which is prevalent in a conventional manufacturing setup, which I have shown on the top left, to what is being seen in this kind of instances, the changes are significant. I mean, the transformation is radical. So fundamentally, if you are talking about additive manufacturing, what happens in this case is the CAD data is converted into a physical model, layer by layer, by adding the material without any human intervention. And if you contrast with the conventional manufacturing, which is being schematically shown on the top left, where in conventional manufacturing, you have to make use of tools, you have to keep removing the material depending upon the part geometry, the process may change, and the fixturing plan may change, and throughout the process, you are generating significant amount of waste, and there may be manual intervention in some cases depending upon the necessity to use tooling and fixturing and inspection, which could be intermediate inspection or final inspection. So contrary to that, in case of additive manufacturing, you are adding the material and the process remains unaffected, even if the geometry is extremely intricate. And the systems can run continuously without any manual intervention. And last but not the least, the kind of materials which are getting integrated into 3D printing systems are continuously on uprise. So in this kind of a scenario, uh, what do you see as the connectivity with between IoT, 3D printing, and other important digital technologies like uh, uh, data analytics, mobile internet, and cloud technology? About 6 or 7 years ago, the world famous thought leader McKinsey has identified technologies which have got ability for disrupting the way the businesses are conducted, the way our day-to-day things are transacted. And as you can see here, there is a big list of very impressive technologies, and you can already feel the impact of mobile internet and robotics, renewable energy, cloud technology in the way we are producing, in the way we are inspecting, and in the way we are supplying various products to points of care. So 3D printing is put in a similar kind of a league, and it is expected, and we have started even experiencing that 3D printing as a technology in tandem with other digital technologies is going to have a tremendous influence on the businesses. So when we talk about 3D printing, we are just talking about a concept. It's not a specific mission, it's a concept of converting CAD data into physical models without usage of any tools. Some work based on the laser curing of photopolymer materials, as shown in A. Some technologies work on the um, principle of extruding a plastic material through a small nozzle, as I have shown in C. It is called FDM 3D printer. This is what is generally seen in many colleges, which convert plastic filament into physical parts. And you have also got other kind of technologies wherein you can project the entire information onto the screen at a single time, and if, instead of discrete movement of the laser beam, you are curing the entire layer to get a physical object. So they come by different names. Some are known as stereolithography, the name of stereolithography, fused deposition modeling, selective laser sintering, laser powder bed fusion, electron beam melting, binder jetting, material jetting, and the other technology is called laminated object manufacturing or layered manufacturing. What is important for you to note down now is this technology is has tremendous ramifications across sectors. I will show some case studies. You will realize how this technology has made significant inroads in India, starting from aeronautics to defense to space research to consumer goods manufacturing to health to transportation, oil and gas, etc. I would like to pick up the examples corresponding to medical industry in particular. There are many orthodontists who are working, including in places like Calicut, Cochin, Hyderabad, Bangalore, Chennai, etc. Wherein, in case you connect with them for their orthodontic treatment, there is no necessity to use metallic braces for correcting your teeth. They take an impression from your tooth, uploaded into the cloud, and somebody who is remotely connected create 3D printed aligners based on the data which has been shared by the doctor. And these 3D printed aligners are shipped within 48 hours to the clinic. And once the patient collects them, there is no necessity for visiting the doctor again and again. In a systematic manner, these transparent aligners can be used, and the correction of the teeth and the movement of the tooth can be done in a very controlled manner. This is a significant representation of the digitization of the entire process in a conventional medical scenario corresponding to orthodontic dentistry. Same is the case with the hearing aids. Uh, Mass customization of hearing aids is possible, and wherein the data corresponding to the ear canals is scanned, and this data is uploaded into the cloud, and the instrument is made conforming to the shape of the ear canal, and the electronics are embedded into that to make a mass customized hearing aid. So in all these things, what is very important is there is a tremendous usage of sensors, optical sensors, proximity sensors. There is a big usage of CAD modeling, 3D scanning, and most importantly, the methodology by which the entire process is becoming toolless. So if you see in this slide, what is indicated here is in case of a conventional manufacturing, you start off with a drawing, you need to develop the process, you need to develop the tooling and machine it, and finally you get the part of your choice. But in case you were to use 3D printing, in one step, you are able to transform the digital data into physical prototype without any intermediate requirements connected with the tooling. Now, what is important is in the olden days, this technology came into existence in the late 80s or early 90s. In those years, most of the initial set of applications were largely confined to prototyping. It means the user groups were interested in giving a shape to the design. They were not really interested in putting the part into use. But in the recent times, we have seen that 3D printed parts are put into real time use, real world use. So I have given two examples, very simple example and most complex example. What you see in the bottom left is nasopharyngeal swab. When the COVID struck the world in a definitive way in March 2020, the number of companies which were capable of making swabs was very limited. And testing was one of the most vital things in terms of finding out the incidents and controlling the spread of COVID. Quickly, the 3D printing companies came forward in terms of producing these nasopharyngeal swabs using tabletop systems and delivering them at the point of care. That is one end of the spectrum. The other end of the spectrum is on the right side, where the rocket engines, casings, rocket engine housings are made using 3D printing out of cobalt chrome alloys, which are extremely temperature resistant, high temperature resistance, and they have been successfully certified for space launch for the usage of the company called SpaceX, started by great innovator Elon Musk. So you can see the spread of applications from simple elementary day-to-day use swab to extremely complex, reusable, large, high temperature resistant rocket engines. So there is use for 3D printing. So in this case, what happens as far as the integration of IoT is concerned? See, when you use 3D printers, you are definitely interested to find out whether machine is running or not, and you would be interested, is there any downtime, whether the system is developing some excessive vibration, is there any hotspot, do we need to change the filament depending upon the consumption of it corresponding to a particular part. So if you're interested in remote monitoring and the operations of the 3D printers, definitely you need to embed the sensors, you need to find out monitoring mechanisms, and you can definitely realize the functional advantages of remote monitoring by usage of IoT. Now come to the other important possibility. When the system is running, you are always anxious to find out whether the machine is running, if at all it's running, is it running as expected? Are there any problems which are likely to rise? So you are interested in the predictive maintenance protocols, and you would like to introduce systems which are smart with reference to the asset management. And the final and futuristic step, which you may not see now, but it is likely to happen in the future, is autonomous manufacturing. Can the machines run on their own without any human interventions? As soon as the feedstock is consumed, can the machine seek the material from the repository, from the inventory, and start the operation on its own? This is a kind of autonomy which you are looking forward to. And IoT practices are very, very important. See, our plant is in Bangalore, and in 7 years since inception, we have served the projects of space, including ISRO, VSSC, LPSC, defense labs for many DRDO labs, HAL, BEL, etc., aeronautical companies including Airbus, Boeing, Honeywell, many automotive companies, healthcare companies, industrial and tooling companies, oil and gas companies. So I'll give some examples from this plethora of options in terms of how IoT integration into additive manufacturing is able to accelerate entire product design and development cycles with the necessary improvement on the quality, productivity, and reliability. So this is a glimpse of our facility at Bangalore. And what we use typically is a technology called laser powered bed fusion. So in case of laser powered bed fusion, um, we are scanning with the help of a laser beam on the surface of thin layers of metallic powders. And when the laser beam gets in contact with these metallic powders, the heat transfer happens at temperatures in excess of at rates in excess of 5000 Kelvin per second. There is instantaneous melting of the particles followed by solidification because the heat gets transferred to the build platforms. And without use of any tools or fixtures, you will be able to make the parts out of metallic materials like aluminum alloys, titanium alloys, inconel alloys, and many steels, including maraging steels and stainless steels like SS316, 174, and 15.5, etc. So what is being shown now is the laser powder bed fusion of a turbine engine which has got a futtery root. You can see after the layer is made, the platform is brought down by an extent equivalent to the layer thickness, and the process continues. Actually, I think because of the bandwidth issues, the video is not playing well. So I'll go to the next slide. So interestingly, this particular technology was born in engineering campuses. So the first ever selective laser sintering system was developed by an undergraduate student called Carl Deckard while he was pursuing his undergraduate degree in University of Texas at Austin way back in 1987. And he was fascinated with this technology. He continued to work with this technology for his master's and PhD. And currently, additive manufacturing business is worth about 12 billion US dollars across the world. Now, what are the products that we have been able to make, and which materials and which sectors? You can see here, we have made parts for propulsion nozzle discs out of nickel-based superalloys called IN718. You can see many sensor housings. What you see in the center is an orthomode transducer. It's a microwave component. It's also called polarization duplexer, used in the RF communication, gas turbine components, and what you see in the right extreme is a part for a Formula student car. And these parts come in different dimensions different materials. Some are as small as 100 diameter. The largest part that we have realized is more than 1.2 meters in diameter, which you see on the left extreme. It is called anti-ice assembly. What is its functionality? It is fitted to a gas turbine engine which propels a combat aircraft, especially when the aircraft is operating in extremely cold zones like Kashmir or Leh Ladakh. There is a possibility that there could be ice formation right in the frontal portion of the gas turbine engine. So this anti-icing attachment or assembly picks up the hot gases from the turbine modules, make sure that the icing is prick-loaded without any repercussions on the thrust levels of the gas turbine engine. Now, what is the use of the IoT? So, what is shown in the top left is one industry grade 3D printer that we are using in Wipro 3D at Bangalore. So, if you look at some of the parts which are shown in the past slide, like a combustor housing, the system has to work for nearly 80 plus hours before a component can be made. I'm talking about a component called flame tube or a combustor housing on the bottom. So it takes about 4 days for the part to be made on a powder bed fusion system on a 3D printer which works with nickel superalloys. By the way, if the same part were to be made in conventional manufacturing, it takes about 6 months. We are able to compress the time frames from 6 months to a week. Now, in the olden days, the entire maintenance protocol was completely different. It used to be reactive. What do you mean by reactive? You used keep working on a system and you can continue to work on the system till it fails. When it fails, you start then looking into the operation and maybe you need to change some parts or modules or you need to service them. Definitely there is a breakdown time and the entire philosophy of maintenance was based on just equipment alone. Afterwards, the technology moved towards a trend called condition based monitoring. It means you are not only dependent on the equipment, you started using some sensors, you also started looking at the processes, and because of this, you are able to take cognitive steps in terms of predictive maintenance. But in the future, what we are going to depend upon is a mixture of, is a synergistic combination of equipment, IoT practices, artificial intelligence, data which is being generated in a continuous mode by monitoring the processes, and finally, you are talking about predictive AI driven maintenance protocol. So you can see here, we are just moving from absolutely reactive mode to completely proactive mode and to predictive mode. And this particular thing has been enabled because of the introduction of industrial IoT practices into manufacturing. We at our own place have demonstrated this concept with a simple concept of how you can do IoT enablement with a Delta 3D printer. I think entire experiment you can just complete in about 2 weeks time, and the expenditure which is involved is also very, very less. Example, if you are making a part out of thermoplastic material using 3D printer where three robotic arms work in tandem for realization of the part, there will be accelerations and the point which you are interested is measuring the temperature on the print bed. And last but not the least, you're also looking at whether filament is in sufficient supply or not. So we could put sensors corresponding to sensing the acceleration, an accelerometer or a thermocouple or a contactless IR temperature sensor. We can have PLCs connect to your gateway, connect to your PC, and you can do the necessary dashboarding in terms of understanding whether the process is happening exactly on par with your expectations in terms of avoiding the excessive extrusion or non-availability of material, alignment of the layers, etc. So this is a very simple demonstration of how you can use IoT technology for monitoring a manufacturing process. And this is something which is very doable. Now, when you come to more complex systems like powder bed fusion systems, what are the factors which need to be controlled? It could be connected with the laser. How the laser beam moves on the powder? What is the laser? What is the velocity with which it is moving? What is the distance between two hatch lines? How thick is the layer? And if you look at something called melt pool, the melt pool is actually is it's a very dynamic phenomena, and the melt pool basically depends on the interplay of inertial forces, gradients in the surface tension, and capillary forces. Incidentally, the heat transfer, as I briefly mentioned, is happening at very high rates in the range of 10 to the power 5 to 10 to the power of 6. And last but not the least, the pattern of heat transfer is not conduction as we generally think, it is more of convection. So if you want to do IoT enablement of this kind of a process, you can see that the current generation systems have started embedding gas sensors, uh, the cameras, and they are getting the data slice by slice. Especially imagine that there is some subsurface porosity which is far above compared to what you had originally expected, or imagine that a support structure which is delaminated because of the reporter movement with a thin cross section module. So all these things can be predicted by integrating these sensors, by integrating the IoT practices into next world generation rapid prototyping systems. It's important to understand that the part which comes out of 3D printer is a function of the interplay among the process properties of the metal powder, and the microstructure is something which you are really interested in evaluating at the necessary points, because when you are able to control the interaction among process, structure, and property, what is possible is the performance of the part will be on par with your expectation. For example, what is shown in this case is a high pressure turbine rotor blade. It has to operate at temperatures in excess of 1000 degrees centigrade. RPMs will be more than 17 to 18,000 RPM. The pressure levels are 20 times more than that of atmospheric pressure. And in case this component fails, the entire aircraft's operation could be rendered into catastrophic. So you can see the power of monitoring the performance and the power of ensuring the reliability through IoT in much big manner. So the other concept which I have come across in terms of demonstrating the applicability of IoT is illustrated here in a schematic way. What is shown in this case is a Delta 3D printer. It is kept in the center on circular tracks. You have got cameras, low cost cameras, and the camera is moving around the 3D printing as the operation is happening. And after the printing of each layer, the data is picked up and being processed on the algorithms of convolutional neural networks. And the entire effort is partially done on the edge computers and partially done on the cloud. And the idea is to predict the defects. The defect could be excessive polymer extrusion or insufficient polymer or hotspots on the build platform or delaminations or misalignments. So this is a wonderful demonstration of how IoT enablement along with machine learning, machine vision algorithms can be done in terms of finding out the defects that are likely to emanate during the course of 3D printing with the polymer. Before getting deeper into the subject of IoT and manufacturing, let me let me spend some time in terms of describing what has been happening conventionally in manufacturing and where are we heading. See, in the early stages of industrial manufacturing, that is 1900, when the company called Ford started assembling cars, the entire focus was only on increased production and reducing the labor cost. During 1960s, the Toyota came into existence in terms of world-class manufacturing interventions, wherein they talked about reducing the defects, reducing the waste, making the entire process lean. 80s were more about flexibility in introducing in the manufacturing. How can you increase the variety of parts? And how can you reduce the inventories without affecting the productivity? But slowly they gave away to IoT enabled manufacturing practices because of significant usage of sensors and humongous improvement in terms of computational capabilities. And because of these embedding of sensors and IoT practices into manufacturing systems, some of the phenomena like improved resource use, uh, machine to machine interfacing, uh, ubiquitous computing, elasticity in terms of improving the responsiveness to the customers' needs. All these phenomena happened, and in fact, 3D printing is one of the manifestations of this phenomena. And the current, I would say, state of the art application of IoT in manufacturing is not about asset tracking or quality control or about predictive maintenance. These are some of the phenomena which have been well understood. Maybe about 2 to 3% of the companies are already into that. There is a long way to go before we can say that IoT is firmly entrenched in manufacturing. In a country like India, I may not be far from truth if I say that the penetration of IoT is less than 2 to 3%. But what is the world's best in terms of leveraging this particular phenomena is a digital twin. What is a digital twin? It's actually a virtual representation of a physical object or a process or a system. So you could be talking about digital twin of a gas turbine engine or a tunnel or a combustor. But only thing is this virtual representation is for the entire life cycle. So the digital twin uses the real-time data from various sensors and other sources to enable learning, reasoning, and dynamically recalibrating for improving the decision making. That's very, very important. So the digital twin is able to continuously learn, reason out, and also recalibrate its response. And all this phenomena contribute to betterment as far as your decision making is concerned. So you look at a complex system like a gas turbine engine. In fact, this particular technology has been championed by world-class companies like Siemens and GE for some years. And when you are able to introduce a digital twin, fundamentally you are visualizing the complex products and systems in real time by disparate users. And if you have made any assumptions with reference to the performance, uh, they get validated, and you're also able to predict the performance characteristics And should there be any problem with any system or a module or subsystem, you can even do troubleshooting from faraway location. So this is one important manifestation of the combination of the IoT practices, artificial intelligence, and data analytics in terms of improving the quality and productivity of the systems. So once again, we made a simple instrument for illustrating to a few colleges in Bangalore how the process of IoT, industrial IoT, can be demonstrated with reference to an industrial need. What is shown in this case is, I think all of us are very familiar with the industrial metrology. So you just get a metrology test rig and get some precision dial gauges, get the data, and you can embed the IoT practices in terms of enabling a methodology by which you are able to measure certain dimensions and take a call in finding out whether the product under consideration can be accepted or rejected or being recommended for certain operations, all these things being enabled in a remote manner. I think you are aware of the fact that many automotive companies, including the Bajaj, Mahindra, the TVS, or Ashok Leyland, they depend on tier 1 and tier 2 suppliers for making the components and parts, and these tier 1, tier 2 suppliers are distributed across the country. In the olden days, these tier 1 suppliers had to physically transport the finished goods to the OEM and wait for their quality control and inspection recommendations before they can get the necessary confidence in the quality of their throughput. But now, thanks to the all pervading presence of IoT, the entire metrology or quality control processes have undergone a tremendous metamorphosis, and you are able to now take real time decisions on whether the product can be accepted, rejected, or recommended for rework because of introduction of sensors into the metrology. Now, as I mentioned, we have been working with space systems in a significant way, and what is shown in this case is the system that we developed in 2017 by collaborating with ISRO, SAC Ahmedabad. It's called Feed Cluster. It's one of the important components of the communication system of GSAT 19. And what you see on the top right is a feed cluster wherein 17 different components which have been conventionally manufactured have been combined into a single part. And this is called monolithizing. It means unibody. So in the bargain, what happened, all the fasteners and weld joints have been given away and it has become a single part. The RF performance became vastly superior in terms of directionality, in terms of gain, in terms of radiation pattern, and more importantly, this particular component has to withstand 10 years of operation in the orbit at about 35,000 kilometers from the Earth, while it is being subjected to wide temperature range changes from minus 30 degrees centigrade to 150 degrees centigrade. And more examples of this kind are coming. In fact, what you see on the bottom left is from a Hyderabad-based startup called Skyroot, which is making the rocket engines for launching of the small vehicles, small satellites. And this particular component has been made out of special purpose aluminum alloy called ALS8NMG using laser powder bed fusion at Wipro 3D. And all these functionalities connected with 3D printing and IoT are enabling the small companies, the large companies, research centers in terms of aiming for higher performance characteristics uh, while the part weight is being continuously reduced. And more importantly, several functionalities are getting integrated into existing parts. Now, if I quickly get into the prevailing scenario, in real world. For example, the what is shown in this case is a snapshot corresponding to the solid waste management in Pune Municipal Corporation. So I think some of you who are very familiar with the smart city ecosystems know that entire waste management is getting IoT enabled. The bins are becoming smart, and depending upon the extent of filling of these bins, the waste collectors are getting the updates. But what is very interesting is how 3D printing has been integrated into that, how IoT practices have been integrating it into this in terms of providing sustainability and the edge of new technology into waste collection. So Mr. Siddhant Pai, who is an MIT graduate, who is a social entrepreneur in Pune, he started a movement wherein the rag pickers are enabled. They can segregate the plastic into two lots, recyclable one and the other stuff, and the plastic waste is cleaned. And then he developed a distributed manufacturing model wherein the plastic can be converted into pellets to filaments, and the filaments in turn are used as a feedstock material for 3D printing. In the bargain, the rag pickers who are simply collecting the plastic waste and selling have become mini entrepreneurs in terms of using the distributed manufacturing models to produce the feedstock for 3D printing. So this is a very wonderful model. And since March 2020, when there was a significant call from state and central government, I have personally seen that many companies, small companies, large companies, medium scale companies, have started using these technologies in tandem with their regular practices in developing medical devices and making sure that they are delivered at the point of care. What is shown in this slide is one of the results of the collaboration between Wipro 3D and Sri Chitra Tirunal Institute for Medical Sciences and Technology. And in this case, we developed one transport ventilator, and it's also called emergency breathing assistive system. And the trade name for that is Airgoods. So the entire developmental cycle was completed between April 2020 to September 2020. Now the product is commercially launched. It's available at a fraction of the cost compared to the foreign counterparts. And the beautiful thing about it is so much of usage of 3D printing, and now we are in the process of IoT enablement so that the transport ventilator can be of significant use to intensivists, to telemonitoring when the patient is being transported from village and Mofussil centers to the metro cities during the phases of transporting. So this is our own example in terms of how a product design and development, prototyping, manufacturing, commercialization, operationalization have been tremendously influenced by the digital technologies. So now the industrial ecosystem is moving towards a synergistic usage of various technologies, uh, s- starting from 3D printing to cloud computing to big data to AR and VR, autonomous robots, IoT, cyber physical systems. We are talking about a scenario wherein slowly but definitively we are impacting the entire process of product development by symbiotic relation of all these technologies. See, when you are talking about specifically 3D printing, we are talking about less wastage, no usage of tools, distributed models of manufacturing. You can say it is almost like a democratization of manufacturing, greater design greater design freedom. Why we say greater design freedom is, in the conventional scenario, we were used to one phenomena called design for manufacturing, DFM. It means even if your design is good, if you are not able to manufacture, then you will change the design. But in the current phenomena, we talk about manufacturing for design. So the designers have got much bigger latitude in terms of experimenting with various concepts and coming out with a configuration that can best serve the purpose. So in this kind of a scenario, what's happening is the digital technologies are slowly but surely getting into industrial context. So this is one example which I have taken from beta type, wherein 300 plus numbers of qualified automotive headlight sinks have been made in a single bed using 3D printing. Out of which material? Aluminum alloy. So the build time has been reduced by more than 90%, and the cost per part is also significantly reduced. So this is one manifestation of the introduction of digitalization into the product design and development. The other example is equally fascinating. I have picked up this example to show it to the audience today from a company called Bugatti, a very famous French company which is into the design and development of premier cars. The part in this case happens to be monoblock. It's a 8-piston titanium brake caliper, approximately 40 centimeters in length. The original weight of 2.9 kgs has been reduced by 40%, and entire processing time was sufficiently reduced. If you see this product, is being subjected to high disk temperatures that result out of high speeds, and it's able to withstand the rigor of real world application. So this is one very important symbolic representation. I have picked it up from the automotive company just to illustrate the point. It could be from uh, any other industry also. Uh, Most of the automotive companies, which have got supply chains spanning across the country, different states or different countries, they have been severely affected during the pandemic situations. The supply chains have been disrupted, and all these modules and systems are interconnected. In the recent times, they have realized that to introduce resilience into these supply chains, it's a must that manufacturing models become as distributed as possible. If you take our own Indian Air Force, it has got fleet which has been traditionally procured from countries like France, UK, Russia, US, and all this fleet, the combat aircraft, the systems are maintained in 7-8 centers spread across the country. You imagine how many spare parts will be there to ensure the conditioning of this aircraft. It could be running into tens of thousands. Now I'll give the third example corresponding to oil and gas industry. For a large country like ours, there are several oil companies including BPCL, Indian Oil, HP, Shell, Reliance Petroleum, etc. And the pipelines connected to the transportation with the supply of oil could be running into lakhs of kilometers or maybe tens of thousands of kilometers. Just imagine that at a particular place, a pump or a valve or a compressor or an impeller fails and you get into breakdown maintenance. So much of productivity is lost, so much of profitability is eroded. But if you were to make use of sensors, if you were to take care of the maintenance in a very predictive way, the entire operations become extremely smart in terms of ensuring the availability of the part on demand, in time, and delivery at the point of care. That's why I see that in the future, the manufacturing processes, the spare part, the maintenance, the spare part supply, all these operations are going to be tremendously impacted because of the integrated use of various technologies into the functionalities. I'll just give two examples before I conclude my talk. About a couple of years ago, the teams from VIT Vellore and IIT Bombay visited Wipro 3D plant in Bangalore. Their idea was to design and develop and topologically optimize and fabricate a part called upright. You can see the upright, it's also called a steering knuckle. It's part of the very important part of the vehicle dynamics. Fundamentally, it is responsible for transferring all the forces that the tire experiences to the chassis and vice versa. It's subjected to steering forces, the driving forces, the lateral forces connected with the cornering, and it's part of the unsprung mass of the automotive system. If you are able to cut down the weight of this part, the cornering efficiency comes up tremendously, and last but not the least, the stiffness also improves. So in this case, we put the component through, and the analysis was done capturing the design context. Optimization was done, significant weight reduction was experienced. Then we converted topologically optimized design into the physical part, and then it was pushed into the test bed. And after getting the necessary confidence in the performance of this particular part, we were able to actually advise the students to go for introduction of this topology optimized part into the Formula Student car. There was usage of tremendous amount of sensorization of the entire process monitoring, and enablement from beginning to end in such a way that the practice can become very smart. So the integration of IoT with the 3D printing is happening because of many reasons, including faster design iterations, introducing flexibility into the production, uh, bringing in more resilience into the supply chain, and enabling customization, maintaining the parts in a very smart way, especially in case of obsolescence and legacy systems. So all these things are enabling. And I just want to conclude my talk by saying that this is a very vast subject. I just want to give you a basic introduction to this technology today. Uh, those of you who are interested in doing more and more work with us, you are welcome. I have many more examples to show, but I would, respecting the time, I will not get into the example. Currently, we are collaborating with IIT Madras, IIC Bangalore, IIITDM, Kanchipuram, BITS Pilani, Goa campus, and so many other institutions with reference to doing projects in additive manufacturing, setting up 3D printing centers, setting up IoT center, industrial IoT centers in the campus. Should you be interested in any research and development connected with the calls of DRDO, ISRO, Respond, DST, or ACT, or DBT, we are collaborating. We are also taking care of some training programs for the faculty and students who are desirous of learning the industrial context of these technologies. And we have also collaborated with a couple of institutions in developing the technologies. So my email is shown here, and I'll be very happy to take some questions for a few minutes. And then if there is any more time, I can present some more case studies connected with the concomitant usage of sensors in complex aeronautical systems. Thank you so much.
Thank you, sir. So, but we have time up to 12:45, sir.
Oh, you have time up to 12:45, is it?
Yeah,
Oh, I thought it's
it's a
about.
one and a half of our session.
Okay. What I'll do is, yeah, I'll continue then. Thanks for the suggestion. I'll continue. Uh, uh, if it is okay, I can take some questions now, then I'll continue.
Any questions from the participants. You can unmute yourself and you can ask any queries. Any queries from the participants? Hope no questions, sir. You can continue, try to continue.
Okay. What were the topics, Shanmugesh, which were handled so far? Because I just wanted to know whether I need to take some more case studies in IoT or additive manufacturing.
In the first phase, we have two 3D printed concepts, but in the second phase, this is the first 3D printing concept.
Okay.
All the other things are IoTs, digital manufacturing. Right?
Okay. What were the specific topics which are covered? If you don't mind, can you tell me?
And the first topic, that is robotics. Second one, we have case studies regarding these IoT devices. Next, we have the IoT protocols. Next, Industry 4.0. These are some of the topics till now we have completed.
Okay. So if I make a small presentation on the possibility of research proposals in close collaboration with institutions, will it be interesting to the participants?
Sure, sir. Sure, sir.
Because I didn't get any response, so I didn't know whether.
In the chat box, you can able to see the chat box. There is some responses.
1 second, I will see the chat box. Yeah, you can. Can you read it out? Because I'm in the full screen mode. I'm not able to see this chat bot. What are
First
you
question,
saying,
can you please give more information about the R&D?
That's what I expected. I
Yes.
expected at least one person to ask on that. Okay. So I'll answer this particular question, then I'll go to the next one.
Also about the collaborations.
Okay. So first I'll take the R&D proposals. See, fundamentally, the funding mechanism from DST, DIDO, ISRO, if you see traditionally it was supporting basic research some time ago. Now the support is moving towards applied research, and there is a concept called technology readiness level, TR level. So DRDO and DST, they want the proposals which have been submitted by the faculty members to be a TRL, lead to TRL2 or TRL3 solutions. Means at the end of the project, you should be able to demonstrate in availability of a product or a process or a system or a device that can meet the requirements with sufficient confidence, and you should be able to demonstrate its operation. Even now, there is a call. That's the reason why I'm very keen to talk about it. There is an Indo-German call involving an industry and academia from India to collaborate an industry and academia from Germany. And one of the focal areas is 3D printing. Other focal area is wearable devices. Third focal area is process monitoring. So I clearly see there is a big scope for integrating IoT and 3D printing and process monitoring in terms of making entire processes smarter and reliable. And the funding is given by the DST, both to the industrial partner as well as an academic institutions, to keep their project goals aligned with these thematic purposes. Similarly, there is one call under DST now called Advanced Manufacturing Technology Call, AMT call. The focus once again is on digital manufacturing and additive manufacturing, near net shape manufacturing. So there is more and more emphasis in terms of sensorizing the entire process and getting it. And when it comes to DRDO funding, the funding from DRDO happens in, if you want to really say, it happens in three modes. One mode of funding is through the research boards. It could be Aeronautical Research Development Board, ARNDB, NRB, Naval Research Board, or it could be from Life Science Research Board. So you need to submit your proposal to these boards. Sometimes in partnership with the industry is preferred. And these boards review once in 3 months or once in 6 months. And if they find your proposal to be commensurate with their expectations, they recommend to be for approval of the board to, to the DRDO headquarters. The second method of connecting with the DRDO is called CARS. CARS stands for Contract for Acquisition of Research Services. So what do you do in case of DRDO CARS project is, if you are someone with expertise in robotics or IoT or Industry 4.0, you connect with one of the scientists of a DRDO lab, which is near to you or which is professionally known to you, and then in association with them, you develop a proposal, and it's like on approval. It doesn't involve big defense, but on approval, it's like a contract. You deliver your research outcomes depending upon what you have declared in partnership with the scientists. That's why it is called contract for acquisition of research services. The third methodology is called ER and IPR. What do you mean by ER and IPR is extramural research and intellectual property rights. In this case, there is no necessity for connecting the proposal with the vision and mission of a particular project. It could be a basic concept, could be a blue sky concept, or it may be a possibility that you are trying to illustrate the process in a new technology regime. So in this case, the proposals are not sent to board or lab, it is directly sent to ER and IPR directorate. So these are the three primary mechanisms of DRDO. In addition to that, there are also specific calls. Few years ago, there was a call connected with the unmanned air vehicles. I clearly remember a lot of organizations which are connected with IoT practices participated in this call. It was called National Program for Micro Air Vehicles, NP-MICAV. It was partially supported by DRDO, it was partially supported by DST, and the research groups in this particular call were involved in the design and development of rotary wing micro air vehicles like quadcopters, flapping wing air vehicles like ornithopters, and fixed wing aircraft to be used in the surveillance applications, reconnaissance applications, imaging, and improving the productivity, monitoring from forests, security areas. So this was once again a tremendous scope for integrating the sensorization for collision avoidance, etc. So this is as far as the special calls is concerned. The one which is extremely interesting to the people who have got interest in IoT and 3D printing is the DBT, Department of Biotechnology, through its arm called BIRAC, uh, systematically and periodically invites proposals under a scheme called BIG. Other one is called PHASE, which is responsible for translating the academic research into commercial enterprises. And the advantage of these calls is the funding is significantly good. So if a student or a faculty member is interested in pursuing the project, he can take off from his duties and become a full-time researcher for the length of the project, and his salary is supported. And in this case, the outcomes could be connected with agriculture, environment, uh, biomedical, or prosthetic devices, implants, um, affordable medical devices, etc. So this is one very important wing of funding which is available in India. And the final one which I would like to present to the gathering today is called Nidhi Abhyas. This is by Niti Aayog, There is also one more wing called the Department of Scientific and Industrial Research called DSIR. In both these cases, if you are an innovator, if you are interested in translating your design idea into a physical part or prototype, they give you the funding to develop proof of concept, proof of principle project, POC or POP. And this funding is not only eligible, not only available to the faculty members, it's also available for the students. And the funding ranges from 2.5 lakhs, it goes right up to about 20 lakhs or more. It's also called seed fund in some cases. And the advantage of this particular thing is you can translate your ideas into working models while you're in the college. So very interesting funding schemes are available. And what I want to emphasize in today's virtual gathering is IoT enablement, sensors, process monitoring are extremely important thematic areas which are being supported by many of these calls. So you people need to be sensitive to these calls. We from Wipro 3D have been collaborating with multiple academic institutions in this regard. Imagine that, in fact, what happened a few weeks ago, a college from Chennai came to us and said that they're interested in converting the transport ventilator into smart ventilator by embedding many sensors connected with sensing of oxygen, carbon dioxide in the expiratory stream, temperature, humidity, tidal volume, peak, flow, pressure, and we sat together and we understood what are all the possibilities of sensorization and how you exactly you can enable it for remote monitoring, and that become a very powerful project proposal for submission to DIRAC. So this is what I would like to briefly say. In case somebody is interested in asking a question, I can give in detail. The method of collaborating with Pro3D is very simple. Send me a mail if you have got interest, and could even be connected with setting up of IoT centers. We are currently setting up 3 IoT centers in Jawaharlal Nehru Technological University affiliated institutions in Andhra Pradesh and Telangana, and the focus is on metrology, performance monitoring, and use of IoT in manufacturing. So I hope I have answered, Shanmugesh. Any other questions before I get into presentation?
Okay, sir. Any other queries from the participants? One more question. There is, if you want to join in R&D department of any company, what steps we do?
That's a very generic, no, Shanmugesh?
Yes, sir.
Yeah. So I think I'll skip that question. That's a very generic question. Yeah. So no other question, right?
No other questions.
Okay. Fine. Then I'll go to the next one
Okay.
in the presentation. So I'm now going to present one very interesting case study which I did about 10 years ago. Uh, this is connected with development of a telemetering unit for a combat aircraft. I think some of you would be knowing that in a combat aircraft, the propulsion is enabled by a gas turbine engine, which is shown in the bottom. There are more than 20,000 parts in case of a gas turbine engine. And right in the frontal portion of the gas turbine engine, we have got this fan unit. Next is the compressor, predominantly made out of titanium. And then we have got a combustor where the compressed air is burnt along with the fuel. Then you have got a turbine where the energy is extracted, and then you have got an exhaust module through which this combustion gases flow, creating the necessary thrust. To really see, the frontal portion of the gas turbine engine is susceptible to foreign body impact, bird impact. Cracks could emanate because of the low cycle fatigue phenomena. And when it comes to combustor, the temperatures at which the gases are burnt could be in excess of 2000 Kelvin. So maybe they develop failures connected with creep. And when it comes to turbine, you have got tremendous amount of centrifugal loads, you have got tremendous amount of thermal loads, and there could be stress corrosion, cracking. And in all these places, there is a necessity to put in sensors for your continuous health monitoring It is called integrated structural health monitoring, and pick up all the sensor data, and from the ground itself you'll be able to monitor whether or not all the modules are expected to perform the way they were designed to perform. Depending upon the class of the operations of the modules, some are called category 0 and some are called category 1, 2, 3, 4, 5. What does it mean is, if a component belonging to higher category is positioned there, means in case anything happens to that component in the form of a failure, the entire mission of the aircraft is likely to be suspended or rendered into a catastrophic mode. So the sensorization is very important. So what we did in this case is, immediately after the system design was frozen, we created a digital replica of the entire assembly. And you can see the multiple components here. The important thing is there are electronics in this component. So it's a must that you need to maintain the temperature to less than 70 degrees centigrade throughout this particular component. And if you look at one of the important design consideration is the size of the component has to be limited to less than 70 in diameter. So we had to go for a big prototyping exercise in terms of converting each and every component into a full-scale 3D printed replica. And if you see in this case is all the components are replicated, including the cooling pipes, and they're assembled. And the entire assembly was checked for its cooling performance as well as sufficiency of the cooling air. And more importantly, we also integrated the lot of customized PCB configurations in terms of understanding whether there is any hotspot, whether there is any fouling, whether entire packaging can be done in such a manner that the reliability of the component is not compromised in any way. And one interesting thing which happened in this case is we introduced one strain gauged simulator, and tested it at about 2000 RPM and trying to understand signal noise ratios and trying to identify the points of stress concentration and trying to identify whether we are able to predict the performance prior to committing our effort to the machine. So if you really see, the design and development of this telemetry unit has taken significant of time and effort despite the availability of 3D printing in terms of physical prototyping, assembling and testing. Now, because of this IoT enablement and the possibility of digital twin, you can recreate components, virtual representations of these physical objects across the complete operational cycle. So what happens in this case is you can create a virtual representation, and you can be getting the data in real time from the sensors which are mounted on the actual component and also other sources. And you can learn and you can reason out and you can dynamically recalibrate the entire component in such a way that you can take the decision regarding to the performance reliability of telemetry unit. So this is one outstanding example wherein you can easily visualize what is the impact of industrial IoT practices corresponding to the complex systems and how do they manifest in terms of improving the reliability of this component and module. Now, the second example and the last example, which I would like to present to you, this was done by one of my tech students about 8, 9 years ago. This was with reference to the customization of the implant. In this case, the patient who had approached an orthopedic surgeon had lost a significant portion of his pelvic girdle. You can see here on the right side because of the cancer, because of the cancerous tumor. And the data was taken using CT imaging and digitally reconstructed into a CAD model. And having done the reconstruction, the entire digital replica was converted into a physical artifact, 1:1 artifact, using fused deposition modeling out of ABS material. And you can clearly see that entire visualization is perfectly enabled because of the 3D printed parts which have captured the complete anatomy. And then we started doing the physical surgical planning with the help of customized implants. So you can see the iteration one. In this case, the wire mesh that you see is a representation of the customized implant. The digital implant, I would like to use the word concept one. Fundamentally, this concept is showcasing one connectivity to the pelvic girdle on one side. On the other side, it is talking about placing this hip joint, including the acetabular cup. You can see here in this concept one, the concept two, which is more refined, and these concepts were tweaked, fine-tuned with the help of finite element analysis in terms of identifying the zones of stress concentration, finding out the locations of the fasteners, and then tweaking the distribution of the mass in such a way that the material is available only at the point of stress concentration and removed from other places. Now, this particular practice is becoming a very powerful practice in India now. There are at least 10 to 12 startups, including in places like Maker Village, in Kerala, Anatomize, in Mumbai, many companies in Bangalore. Fundamentally, if you upload the data which is taken from scanning of some anatomy, now you are able to get physical parts, including patient-specific surgical guides, implants, both from metallic materials as well as thermoplastic materials. And the surgeons are able to do the necessary rehearsals on these anatomical replicas before getting into the real situations, which is improving A, uh, the efficiency of the surgery, B, it is reducing the trauma for the patient on the such vote. So this is a very important intervention, and I'm seeing in course of time there will be many sensors which are going to be embedded into these practices, and there will be a lot of tactile sensors, and the surgeons are using them as good pedagogical tools in terms of improving the skills of the medical students. So the we I have also taken this as a pedagogical model for improving the quality of thinking of the students. I've been member of the academic committee subcommittee of National Board of Accreditation for nearly 7 years now. I've really seen that when people talk about outcome-based education, fundamentally they connect it with MBA. But important thing is, if you really look at the Bloom's taxonomy, the students typically try to remember whatever they have been taught. And in some cases, there is an effort to understand and apply. But when you want to improve the higher order skills connected with analysis, evaluating, and creating, the efforts by the faculty members are not really significant in the classrooms. Most of the efforts are limited to only remembering, understanding. Sometimes it may go up to the level of applying. So what I have seen is the technologies like IoT and 3D printing can be used in tandem in terms of translating the students' disposition towards the subject from applying to analysis to evaluating and creating. How does it happen? I'll give one example. Shanmugesh, if you don't mind, I'll give this example for about 5-6 minutes and close the talk. I hope to at least take some 3-4 minutes of
Okay,
Q&A.
sir. Okay, sir.
Is it okay? Because I don't
Fine.
want to be talking till 12:45 without really understanding whether faculty members are interested in learning more. So I'll just try to conclude my talk by 12:40. If it is okay?
Okay, sir.
Yeah. So what we have done in this case is, if you really see on the right bottom, what is shown here is the ornithopter. As I briefly mentioned, it's a mechanical bird, and the important segment of this mechanical bird is a flapping mechanism. A flapping mechanism converts the rotary motion into flapping motion of the wing. So if this flapping motion happens at about 15 to 18 hertz, the ornithopter will stay airborne. It will generate the necessary lift, necessary thrust, and it can carry some sensors, including visual sensors, IMUs, and you can do imaging using the, the ornithopter. Fundamentally, I introduced this as a part of the exercise to be done by third semester students right in the early stages when they got into the branches, and gave them the freedom in terms of exploring various designs for converting simple ideas into working models and making the ornithopters to operate. And I saw that this made these sessions extremely uh, interactive, and these sessions are called active learning sessions. What do you mean by active learning sessions? Is student is not simply the recipient of information, he is trying to apply that knowledge for realization of a physical tangible system. So there is a translation of the learning into the physical system. So I used to see that the connect between this ornithopter model and the student was immense, whether he's from computer science or electronics or mechanical, aeronautics or electrical, because it is giving him an opportunity of converting the fundamental knowledge about physics, mechanisms, fabrication, machining, and sensors. If you really want to do some more experimentation in this case, you can introduce lidars into this, and you can introduce low cost visual sensors into this, and you can do, you can operate this component in GPS denied environments, including indoor environments, and you can explore the design and development and application of algorithms for simultaneous localization mapping. I think some of you who are from electronics and computer science will be knowing this technology called SLAM, and you can get the data, and the flying vehicle will be able to assess the pose with reference to the environment. At the same time, it will be able to map the unknown environment, and simultaneously it leads to completion of both these tasks. So with the help of these low cost sensors, low weight sensors, which are available today based on the MEMS, you can think about doing this kind of simple experiments, embedding the practices of design, 3D printing, IoT technologies, data analytics, and make the students and make the faculty members to be very genuinely connected in terms of translating the knowledge into uh, working level systems. I think, Shanmugesh, with this, I would like to conclude my talk. Um, uh, and then I'll be happy to take the questions for 4 or 5 minutes. Hello. Hello.
Yes, sir.
Shanmugesh, I said that I close my talk now. It's about 12:40. If there are any questions, I'll be able to take the questions for next 5 minutes.
Okay, fine. So any queries from the participants? So if no other question, can we wind up, sir?
Yeah, thank you so much, Shanmugesh.
Thank you, sir. Thank you very much. So without much delay, let me invite Mr. Lavin Verghese for the vote of thanks.
Good afternoon all. I take this opportunity to thank Dr. U. Chandrasekhar sir for giving informative section on industrial IoT and its application, and sharing information regarding R&D and funding related topics in industrial perspective. I also thank the participants for the cooperation and smooth running of the program. Thank you all.
Thank you, sir. Thank you once again.
Thank you so much.